We present post-aware self-supervised learning with viewpoint trajectory regularization. In this video, we see the car is heading towards us, and we might be at danger and want to jump out of the way. As the video plays, we can see the car actually is heading away from the camera, so we are not at danger anymore. This reminds us recognition needs to understanding two aspects. First, what is the object? And second, how it is presented. We want to learn disentangle semantic and pose representation such that on one axis, the object line up on the identity part, and then on the another axis, the object is lined up on the object pose. What should be the setting for learning this disentangled representation? Consider a scenario where a robot moves around in the environment and sees these videos. A nature data acquisition scheme is that there's no labels, but we do know the adjacent images of the same object from a smooth viewpoint trajectory. Because there's no label, it's great to understand self-supervised learning, or SSL. Existing SSL, such as VicReg and SimClear, learns invariant representation and captures object identity only. When the object changes the pose, the representation collapses to one point. We want to learn equivariant representation that captures both identity and pose, such that when the pose changes, the representation also forms a trajectory. Why is post-aware supervised learning so hard? First, there's no such benchmark, so we propose a benchmark to evaluate and study this problem. Second, there's no method that avoids the representation to collapse on different poses, and we propose trajectory regularization to alleviate this issue. Our data considers a combination of semantic and pose. For semantics, we consider in-domain categories and out-of-domain categories. For each object, we render them of different poses, and if we represent them on a Waving sphere, we can visualize the in-domain pose and out-of-domain pose in the spherical coordinates. The task consists of the semantic classification, absolute pose, to understanding the global pose performance, as well as relative pose, to understand the generalizability. Please note that there's no need for category-specific pose for relative pose estimation, and this method will generalize to open and unseen categories. For the learning part of the self-supervised representation, first, we just use the traditional invariance learning. For example, in VicReg, we can use different augmentation to this image, such as crop and jittering, and then ask the representation to be same for semantic representation learning. For geometry, we present the representation of three images, L, center, and right, and get their representation on a feature hypersphere. We can find their difference vector V1 and V2 and project them onto the tangent plane at the center representation ZC and get a projection U1 and U2. To line up these three embeddings, we can just minimize the cosine similarity. Self-supervised representation learning, finally, loss is a combination of the semantic loss and the trajectory loss. After training the representation learning method, we can get a representation for probing, such as for classifying the semantic and pose labels. The results shows that adding trajectory loss outperforms the baseline method. Additionally, self-supervised learning is close to the supervised method. For out-of-domain result on pose and semantics, we also see a similar trend when adding the trajectory loss. Additionally, SSL generates better than supervised method on the For multi-class representation, we can see the representation of different semantic categories are grouped by their hierarchy. When we zoom in for airplane, we can see a single class representation are grouped by the pose. As the airplane pose change from 0 to 33 to 90 to 158 degree, the representation also changes. So there's an emergent post-semantic representation without any label. Compared to the baseline, when adding the trajectory regularization improves the pose understanding. And this leads to us similar semantic accuracy, but much higher pose recognition accuracy. Thank you, and please come to our poster at number 256.